Okay, so let me see. So Kala is asking for homework question 16, 18, and 19. I'm gonna go through that. And then they wouldn't go much with the finite work compensations. What is new Z and psi C? Yeah, here's my experience with the question in the exam. He's not going to give you a very complicated problem. So if it's were to be a finite well problem, it's gonna be something very simple, something that I think would most likely be a qualitative question rather than a quantitative one, because true solution for for a finite square is not that easy to derive fully in under 2 hours, right? And so let me just grab this book really quickly. So if you guys can just go onto the internet right now, if you guys have access to the internet, just type this in, search for this book, third edition or second edition, it doesn't matter. And you guys can just like read through a little bit, like skim through chapter two. Chapter two is basically a lot of the problems that you guys have to do for the quantum mechanics section of this course. So it's very easy. If I remember correctly, 2.6 is for the finite square well. The finite square well is not like a very difficult thing. Um, and this book did a decent job at kind of like, go through it. So once again, the book is Introduction to Quantum Mechanics by Griffiths and Schroeder. So I can actually send you guys a link here. Actually, let me see. Uh, yeah, here you go. So third edition, this website gives you that. So uh, it's available on the internet. Just go to chapter two. And chapter two has like basically one-dimensional problems, similar to what you guys were doing in the last like few weeks. Basically, harmonic oscillator, finite well, and infinite well, finite barrier, and you know, trap like a trap atom, like a trap atom inside of an infinite barrier. So those are the kinds of problems in chapter two. It's very similar to what you guys have been going through. Yeah. Yeah, define it well fully is very rigorous. So it's okay. Will we have to deal with the two? Yeah, so I don't know. The truth is that I don't know, but it's most likely it's going to be one dimensional or two dimensional, because three dimensional is very usually very cumbersome, and so he want. I mean, if he want to ask something, he would most likely ask quantitatively for a 1D or 2D problem. If he were to do a 3D problem, it's most likely going to be a qualitative one, which is a one or two sentence answer. Yeah, I just want to check if you guys like understand that concept. Yeah. So actually, let me thumbs up the things that I've answered so I know which one I have done. Okay. Yeah. All right. So if no other question, I'm just gonna go back to question 16, 18, and 19. Um, but I need to figure out how to connect this to the meeting first. So let me forward this link to forward my email. Nice. Okay. Oh, wait. Oh, sorry. More questions coming. Oh, no, there's not. That's the older questions. Okay. Because I have to approve myself. There we go. Nice. Okay. Okay, so I'm gonna share screen on this one. Okay. Okay, can you guys all see what I'm drawing now? Oh, it's a whiteboard. Okay, wait, hold on. Maybe this is something that everybody can draw. Okay, maybe not this. Not this. Hold on. Oh, not the best. Sorry, guys. I'm not very good with this. Okay, actually, let's share screen. Oh, only the host can share this meeting. Okay, let me get myself. Now I feel the pain of being a professor or a teacher during COVID. Let's take a look. It's not like for every the hell is it? Make co-host. Okay. So let's share and then screen. Hold on. So let's do freeform. Freeform. We just do this. Oops. Okay, I'm gonna share. Sorry, guys. It's okay. So sorry. Okay, let's do this. All right. So you guys can see, right? Nice. Out of the way. Okay, so let's do question 16. Oops. So question 16 is, let's take a look at the what it asks. Yeah, so it's the harmonic oscillator and the raising, lowering operators. Yeah, so this is so I just want to let you guys know that it's worth writing a good cheat sheet. And what that means is that just put down like the like general equations that are useful for each of the components of like the 1D or even or what just 1D quantum harmonic oscillator and things like that. So actually I can what I can do, hold on, let me I can send you guys a copy of my cheat sheet at that time. So you guys hopefully can see if it's useful. I'll do that later. I'll do that later. Um but okay, so let's do this. So so we know, so SHO, right? We are dealing with an simple harmonic oscillator problem. So we have V of X is equal to X squared, right? Now, so raising and lowering operators, like as you guys know from class, they are not observable, so you guys cannot really extract anything physical out of it, right? But you can do what you can do with it is you can manipulate the system, the harmonic oscillator, in a way that you can excite it discretely by one level at a time, or discretely lowering its energy at one at a time, right? So if the lowest energy here is gonna be um, half H bar, you have other things, other energy levels, then each of the H or A uh, dagger is gonna be lowering. Oh, sorry, it's gonna be excitation, and A is gonna be lowering, right? So, and this is gonna be excitation, right? And so this is meaning going up and this going down. And so I'm just going to recall this. Okay. So I'm just going to rewrite the position operator X as represented by raising and lowering operators, right? So it is equal to, right? By the way, please stop me if I do something wrong. So that I don't carry on the wrong until the end of this. Well, let me write this. Amen. So um, in this case, A plus here is just this, okay, and A minus here is equivalently to that, okay. Um, I just want to make sure that we have this down, okay. So this is our convention for the rest of this problem. Okay, so what are we going to do now? So what we are going to do is that we are going to apply um, this notation, right? So we've tried to find the potential energy expectation. So what we do is that we apply the operator on top of the ket, right? And then reproject the entire thing on the bra of that state. So what we have is that we have, let's say we have state and right. So right. So what we can do is we can say, okay, I'm gonna do real x is equal to, right? I'm just pulling out this 1/2 mass omega square, right? And what? Because V is equal to 1/2 mass omega squared x squared, right? Omega is just omega. Mass is constant as well. A half is constant. So I'm gonna find the expectation of x squared, right? So what I'm gonna do is I'm gonna write x squared down, right? Now x squared is operators. So they apply to the state n, and then you reproject that, right, on the bra of n to find the potential energy, oh, the expectation value of x squared. So this is equivalent to our potential energy as defined above, right? So this is the potential energy, and this is our new results, or not result, but like our new representation. And from there, let's do substitutions really quickly. Um, because earlier we have that. So this squares, right? This square root, right? Squares gives you and then you have this thing, right? Note that these are operators, right? A plus and A minuses are operators. And so let me see if some other people is joining. Sorry, uh, just have to remind myself to do that. Um, oh, sorry. Yeah, it's was meant to say that it's not like this, but rather because it's x squared, right? So we basically we sandwich it between the bra and the ket of our state that we want to find the um, average value for. Squared this off. Okay. Right. So now we evaluate this. So we expand this. After we expand this, right, what we see is that there will be some terms like this, like, oh, sorry, oops, A minus, um, A plus, A plus, A plus, A minus, A plus, and A minus, A minus, right? We have all these terms. Now, I have a question for you. So, um, which one do we consider? Which one do we not consider? Uh, just chat what you think. May- yeah, exactly. So we consider always consider the mixed terms, right? Why? Man, this might be the start of my Twitch career, you know? Doubles will be yeah, yeah. So um yeah, so let's follow Andrew. So we have this, right? And we also have this. Okay. And so if we consider only those two, then what we'll get is we'll get a 1 over 2 times by 1 over 2 h bar omega. Um, so, oh wait, yeah. So let me quickly explain why Andrew is right on the orthogonality, right? So let's think about this. For 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 every one of these, so let's say that you have A plus, A minus, right? If you evaluate it on n, what do you get on this one, right? You get, let's say that we first apply this onto n, we got n minus also n minus one, right? A n, right? Right. So we have a plus applying on n minus one and n, right? After we apply the a minus already, we applied a plus now. A plus give n minus one to n, right? So we remember this. Remember we have like, let's say this is n minus one. This is n. This is n plus one, right? A plus will give n will make n to in equal to n plus one, and a minus will make n into n minus one. And so after this applied to this, we have what? We have n n minus one plus one, which is n, right? And this is now evaluable. We can evaluate it, right? In the case of something like two pluses or two minuses, which Andrew correctly pointed out that is not viable. Why? Because if you do a plus, right, on n, right, you apply once a plus one to n, you get what? You get n plus one, right? And then after you apply this a plus onto n plus one again, you get what? You get n plus two and n, right? Now this is, can we evaluate it? We cannot, right? Because they are orthogonal. All of the states in the harmonic oscillator are orthogonal with each other, and therefore, if you evaluate anything, right? If a whatever operator you want to put in here, let's say q, right? B, if a is not equal to b, right? Then this entire thing is zero. If a is not equal to b, right? If the two states are not equal to each other, it means that they are orthogonal, meaning that the moment you do the inner product of them or applying and then reproject, you get cosine of nine. You get a sine of zero or a cosine of 90, which give it zero. So just remember this, right? And from that, that's why we have to eliminate all the terms with the plus only or the minus only. We only consider the cross terms, right? And so after we apply the cross terms, do it yourself. But what you do, what you get, the correct answer is h bar over 4 times by 2n plus 1. Okay? Because you this h bar omega n over 2 is from the like half energy of each of residue half energy of each of the levels, and then the h bar over 4 term is like the lowest energy level of the harmonic oscillator. Okay. Okay, let me see your research case. There are special cases where the operator makes B non-orthogonal to A. Yeah, yeah. So let's say that you want to calculate this, right? N, and then you have x, which is the positional operator, right? And then you have A plus a dagger, which is this thing is equal to A plus, right? And then N minus one, right? Well, how do you evaluate this, right? This is equal to what? To N. Now you apply firstly A dagger onto N minus one, which make it into N, right? N minus one plus one is N. And now you have X. So this is absolutely, calculable, right? You can absolutely find this, right? Yeah, it definitely works. Now, one can say that, okay, so X hat, A hat dagger is equal to Q. So in this case, Q hat is absolutely calculable between the two states, right? I know. Yeah, so usually when you meet a question like this, right? Like say P hat star, which is the conjugate of P hat, right? And X hat, what you can do is that you can re-represent, right? So re-represent this in terms of A hat and A, right? Re-represent it in terms of some function F, that is a function of A hat and A hat, A hat and A hat dagger, and then use that to apply onto the states. Deal? Okay. So you guys want me to remind you of what that is, like what A hat and Hey represent? Like, okay, so I'm just gonna quickly note down. Okay, so um, P hat is just basically I H bar omega mass, right? Over two times by A plus minus A minus. This is the representation of the P operator. The X operator is similar. It's just two, like we defined earlier here, right? We have where's the X? Yeah, so we have H bar over 2m omega. So H bar over 2m omega, right? A plus plus A minus, right? So this is like the two representation that you guys should write down onto your cheat sheet so that whenever you meet like a problem with harmonic oscillator and they ask you to find, let's say, XPX, right? You guys can re-represent this in terms of these, and then use the um, the ladder operators to see if to cancel out the orthogonal pairs. Okay. Yeah. Okay. So I'll zoom out a little bit so you guys can see the whole picture. Um, so that is the first part of question 16, which is the expectation value of the potential energy, right? Very similarly, we can also do the same thing for the kinetic energy, right? So 16b, we have the kinetic energy, K, right? Which is KE, which is a half mv squared, which is more commonly known usually in intermediate physics as p squared over 2m, right? Now note this down because this is very important, right? Kinetic is usually p squared over 2m. It's a very common thing in all of mechanics, classical and quantum. Once again, we use our little representation over here for p hat, right? So we have minus one, right? H bars, oh, sorry, H bar omega m over two, and then a plus minus a minus squared, right? And so after that, what we do is that we do the same thing. Now, because we want to find, let's say, KE average, right? We can find, okay, so this is just equal to p squared over 2m average, right? Because 2m stay the same the whole time. It's just gonna be p squared average over 2m, right? And this is equal to what? It's equal to the average or the expectation value of this, right? So how do we do that? It's just gonna equal to for our state, right? So let's put here for our state n, right? some arbitrary state inside of the harmonic oscillator, right? In right, just some random state. It doesn't matter which state it is, right? We have more state above and below it, right? This is some arbitrary state. We're just gonna do, right? That is the bra of the state. Now we're gonna substitute the entire thing here into the p squared. So we have -1 h bar omega m over 2, right? And then a plus minus a minus square, and then n, right? And then after that, just going to be 2m over 2m, right? Similar to the last question, which is rather than using x squared for the potential, we're using p squared for the kinetic term, right? And after that, if we remember our little thing earlier, right? A plus, and a minus will give our state because we evaluate it from n and n here, right? This is n and n state. These two is going to give mismatches, right? It's always going to give these two is always going to give what? N minus n plus 2, which is equal to 0, or n minus 2, right? Which is also equal to 0. So the terms with the minuses only or the pluses only, because of the working out like earlier, is always going to give 0. So we know that those terms does not contribute. Therefore, we only consider a plus, a minus, and a minus, a plus. These terms are the one that we will consider, right? And so after you guys do that, let me just quickly show. So that's what we did, right? Earlier we did the right thing. By the way, all these things, right? They say the same, so we can pull them out at the top, right? And so rewrite them. It's just going to be -1, that entire thing, right? And then n something some combination of our thing, and then over m, right? The entire thing is over 2m. So this is an entire thing, which is like the average kinetic energy. And then after this, right, you should also find that T or K E is also equal to h bar over 4 2n plus 1. Okay. Oh, sorry. This is okay. So this is also the standard value for the kinetic energy terms. Yeah, no. So the 2n is this. So this is a standard solution. Okay. So if we were to do out to like do this entire thing out, this is what you will get at the end. So this in a less simplified term is going to be h bar n over 2 plus h bar over 4, something like this, right? And this is the result of us using the so what we do is that we evaluate this entire thing. Oh, sorry. Oh, oops. So if we were to evaluate the entire thing, this is the formula that we will get. I strongly recommend you guys to do it yourself, but I mean I can try to do it. So it's let's do it. We can do it. Yeah, we can absolutely do it. H bar m over 2, right? Now a plus minus a minus, so that gives us 4 terms, right? A plus minus a minus a plus minus a plus a minus, and then plus a minus a minus, right? Now we know these 2 terms are out, right? So they're gone. So what we only consider are the 2 terms. And what it means is that we will evaluate now h bar m over 2, right? Oops. Yeah, I don't know why, but this app, like, it's always just try to correct me for some reason. Times by 1 over 2m, right? Times by A or minus A, sorry. A plus A plus. Okay, let me do this. Like minus A minus, right? Plus minus A plus A minus, right? Now this thing becomes what? Becomes something, right? If we look at our definition for the thing, oh sorry, I missed the minus one here. Sorry. Yeah, this I can delete this. Okay, so this, what does this become? They become n, right? You so a plus acts on n gives you a plus n plus one, right? And then minus a minus act on n plus one gives you minus, right? So it's just gonna be like this, right? Now this is one, it's minus one, right? Similar to this thing is the same thing. N minus one, a minus makes n into n minus one, and then a plus make n into n plus one again, right? So n minus one plus one is n, right? So we retain with this, and then this also becomes minus one, right? So this entire bracket gives you minus two, right? This entire bracket. And so if you go down here, you see that it's equal to minus one h bar over 2 times by 1 over 2m times by negative 2, right? Now if you do the thing, if you do the math, you get so the minus comes out. So it's h bar m over 2, 1 over 2m. Oh, sorry, the 2 here is gone, so 2 here, so just 1 over m, which is h bar over 2. For the case that there's no n. If there's n, then it incurs. So this case, you can see that there's no n in our final results because we are considering that this is like an end state. If we were to do say n plus one, then we can have a recurring formula for all n's, right? A recurring form, or not a recurring formula, but like a general formula for the kinetic energy for all n's, and that formula would be this formula, okay? And so that's what it is. Okay, deal. Let me just mark all this. Oh, it seems like there was like one more person trying to join, but then I didn't click accept. Yeah, I didn't. I tried to do it, and then it's like they don't connect anymore. So I don't know what happened. Okay. Okay. Any other questions on how to do this? Yes, the formula should be identical. Right. So the way that you work out this thing is, I think, is correct in this way. The n is usually because so there's a so I don't know if you guys have heard this in the class, but there's something called a number operator, and right, and that thing is usually something that you can apply onto your states to extract this, right? And this operator is usually I'm not I'm not con I think it's this one. So yeah, yeah, this is the thing. Yeah. So you were right. You were right. You were absolutely right that I did one step wrong because a um, dagger A is A plus times A minus, right? Which is this one, which is definitely not minus one. because this thing is one, and because of the minus, it's equal to minus one. But this thing is also equivalent to the number operator, which gives you n. So that's why this is n, and it makes our formula a little bit different. And actually, that's why it was in this form. Yeah, you were right. You were right. It's actually my fault to not introduce this. Yeah, I kind of messed it up a little bit. Sorry. So it's equal to minus one minus n, right? And because of the minus one to start, you just rub that out, and then you got 1/2 m times by h bar omega m over 2, right? The m goes away, so you got h bar 1 plus n over 4 over 4, right? And so that's our story, right? Yeah. So this is our yeah, you're right. So this is the final results, like I said before. I mean, in my solution, I usually just summarize it, but yeah, this is the one that we were talking about earlier, right? So this is equivalent to that, right? Oh wait, that's two n plus one. Where's two come from? No, that's sus. That's kind of sus. Okay, but yeah, just accept this. I think this is the correct one. Yeah. Yeah, so okay, so the n hat is called the number operator for the SHO. And if I remember correctly, it is defined as a hat dagger a hat. Yeah, can you check it really quickly? Actually, I can check it really. And okay, so what does this number operator do, right? What it does is that its expectation value is n. Okay. A plus. Yeah, maybe Andrew is right. I might be missing out this part because I thought that this is minus. This is one. Like it's been a while. Yeah, yeah, you're right. No, what Andrew says sounds kind of right. Yeah. So let me check. Yeah. So the latter number operator is not small n, but it's actually big N, and it's defined as a dagger a. And so similarly, you can also define or so okay, so I'm just gonna write this n, which is the number operator. If you act on a ket n, it's gonna give you the eigenvalue n times by that ket, right? Because the eigenvalue n is like the eigenvalue for this operator, which is the number operator, and the number operator is equal to a dagger a. You got it? Yeah, 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 yeah. So a hat, like I'll say, sorry. So a hat, or like earlier we said, a hat is equivalent to a minus, right? Yes, you're right, Kala. You're right. Yes, correct. This is correct. It's correct. Yep. Yeah, and Andrew's right. Yes. Okay. And then for completeness, a dagger is just equivalent to a plus, right? Okay. Okay. Yeah, I could be very rusty on this stuff because I didn't redo everything. I just because they're the same questions, so I just take a look at my old solutions. But yeah, freshen up. Okay, sure. So I don't have any I don't know what qualitative question that he would be asking, right? But what I can maybe what I can give you is say um let's think. Let's think about what I can ask you in terms of qualitativeness of this quantum mechanics. Because he usually asks a very usually a very trivial question. Yeah. That could be the case. Right. So okay, so let's do that. So let's say that so can some of you describe like maybe if I had to have like this system, right? Yeah, X here, and then you have V here. If I have this system where this thing, right, is like a barrier, right? And then you have a wave goes in here. What happens inside and what happened outside, right? So like we know already, what happened inside is that the wave will attenuate, right? Exponentially attenuate, uh, decay, and is another word, right? Inside of the barrier, and then after that, it will retain its sinusoidal form. So this could be something that he kind of forces you to sketch, right? Or something like this. So maybe something like right, something like a barrier and then a whale, right? Now, I've seen this before in undergraduate quantum mechanics. It's actually a trick question where the wave come in or the particle come in this way, right? It's in the form of a sinusoidal wave. It will attenuate, right? Because it hits this barrier, right? Cool. But then after it travels for a while, right? It goes through this well. I mean, uh, for some reason, student put like a very weird shape for this part of the well, like maybe like something like this or something like this. Like, I mean, you guys should know that because this is the case where the particle has more energy than the well, anyways, right? It's not a bound state anymore. So there's no bounding, right? The particle is completely free. So it just continues sinusoidal, right? It's there's no change in the wave function in this area, right? It doesn't matter. It's as if the well doesn't exist, right? Or there could be a case, right? And just remember this for reference. It's just like let's say that the barrier is a triangle, right? Similar goes in, right? And if you guys remember correctly, like from last time when we would first met, right? The pattern is called the Airy pattern or the Airy function, right? Inside of the wave. You guys don't have to remember this, but I think it's like also an attenuation like this, but it's less. It's not exponential. It's like slightly exponential-ish, right? Yeah. So the barrier isn't bound, so there isn't any quantization. Exactly. Yes. So there's no quantization if there's no bound. Okay. Um. Yeah. So if you remember, yeah. So that's yeah. You're correct. Yes, this is correct. Okay. Values after attenuation. Values after attenuation. So if by values you means boundary condition, then yes. If he were to give you a real quantitative problem that you have to solve in terms of finite barriers, he will have to give you boundary condition. Otherwise, you don't know what to fill in for A, B, C, D, E, F, right? Because you have six terms, two for each of the regions, right? You need boundary condition for figure it out. Yeah. So what we know whether way below. Yeah, exactly. Yes. So he will have to give you in terms of if it was a quantitative problem, which is a written out problem. A qualitative problem is usually a lot less mark, and it's usually just there to check your comprehension of the idea instead of forcing you to calculate anything. So it's the case that he's just gonna tell you, okay, maybe sketch this, right? Okay, so let's see, Kali. Should we show that the amplitude decreases? So so here's the thing. The amplitude depends on what, right? The amplitude depends on the coefficient. So Usually, um, I don't think he cares. I don't think he cares because usually it does. Technically, it does change, but only slightly. Yeah. So it doesn't matter. Yeah. As long as it's very clear that inside of the well is attenuation, outside of the well is sinusoidal, I think you get full mark for such a qualitative problem. Yeah. Does that answer your question? Okay, good. Okay, let me mark this. Very nice. We've already mentioned something about above define it well. Yeah, so if the well is like a finite well, then it wouldn't actually this is a very interesting problem. Like this is why I like to do TA because you guys ask very good question and it makes me have to think about I, I think it will affect this wave in the case that if the well is a infinite well. If the well is infinitely long, infinitely deep, then it usually there could be a chance that it will be bounded. I'm not sure. That's my intuition, but I'm not sure. Let me quickly just check the book. Maybe not in this book. This book is not good enough. But for the vast majority of finite wells, as long as it's unbounded, you don't have to worry too much. Yeah, let me check. But for now, just give me like 1 minute. I will check it. Oh, by the way, just before I check this, have you guys go through something like a delta function barrier, like this type of barrier, where the barrier is infinitely thin and is like infinitely tall as well. Like, how do you deal with that? Yeah, this is called a delta function, by the way. So delta function barrier. Have you guys deal with that? Or did he ever mention it? This is called a yes. Okay, good. So you guys know how to deal with this kind of problem, right? Okay. So it was finite in height. Yeah. For all of the cases of these things, right? Put down the formulas. Put down the formulas for the cheat sheet. Okay. Yeah, it is in Griffiths. It's because you are allowed one cheat sheet, just put them so that it's there. And so in case that you guys, don't have you're a little bit short on time in terms of like trying to remember what it looks, what the maybe the shape of the distribution looks like. Just copy that. You don't have to remember it in real life. Actually, yeah. So just it's worth putting down into the cheat sheet. Yeah. So just put down all the standard solution for finite and infinite wells and infinite and finite barriers, and you guys will be fine. Yeah. Oh, yeah. Okay. Potential step. Okay. So potential step is a little bit different, right? It's this, right? So it's a little bit different. Yeah. Or it could be a step down as well, right? It could be a reverse heavy side. So it's a step down instead of a step. That's fine too. Yeah. 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 The solution is actually very similar, right? So yeah. Because do you know why I asked this question? Because earlier I know that this type of well will not like have a massive effect on the particle in real life. But in real life, if you guys were to have a well that is so small, like let's say that you have a well, let's say you go like this, right? And then you have a well that is like so deep, like infinitively deep and infinitively thin, right? And you have a particles goes like this, right? It will matter because what will happen is that there can be scattering. there's a chance that the particle or the wave of the particle, the wave function of the particle scatters from such a wave. And so this problem is called a delta well or delta function well, delta function well scattering. Yeah, and this could be a problem. This could be a real problem because when this happens, you have to consider like A and B coefficient. Um, so let's say A is this way, B is this way, and then on the other side of the well, right? On the other side of the well, you have to also consider. I don't think he has mentioned this in the class because this one is like for physicists, like physics students. But it's usually the case that you have to reconsider your entire wave function, similar to the case as if there's like a finite barrier here. Like you have to consider reflection, transmission through this infinite barrier. And like if you already can see it, D and E, oh sorry, or C and D, which is like the coefficient for the equation inside the well doesn't exist because this well is zero in width, right? It doesn't have a width. So there's no wave function exists inside of it, right? But you have to consider scattering. Yeah. So this could be a problem. But I think for all that you get, what I could misremember. Could would delta potential be? No, it will not. It well, yes, it will be similar. Yes. So yes, this is correct. How do I spell your name? Jelgen? Alp? Yeah, don't worry about it. Yeah, yeah. So yes, you were correct. It would be similar to the infinite potential well. In the case of an infinite potential well, C and D would be could be finite. Could be something that is finite. Yeah. Uh, and you can transmit through delta potential. Yes, yes. You can transmit. There will be a transmission coefficient as well as a reflection coefficient, right? Um, yeah. So usually, I think if I remember correctly, the transmission. So let's consider this case, right? We have A, B, C, D, where the well is infinite. Usually, it's applied to doesn't matter if this is a well or a barrier. The transmission, the transmission is usually like defined as F over. Oh, sorry, as E over A, right, squared. And then the reflectance of the barrier, or this is a transmittance, and this is the reflectance of the well is defined by F over B squared. Yeah. So this is usually the case if you have like a barrier, like a delta function barrier or delta function well. Yeah. You define the T is like the transmittance and reflectance of what of the barrier, right, or of the well. Yeah, it could be B over A. I oh wait, no, it's usually the other case. It's usually like how much has go through from the start. Yeah, or this is specific. Reflection is B over A, isn't it? No, no. If I remember correctly, which I think I am here in this case, I think it's usually you're comparing the how much that is appear on the other side with respect to how much it come in at the start. Okay, so that's how I would define it. I think this is correct. I don't think it's incorrect. Yeah, let's see. By the way, for those of you who check out the link earlier, for finite square well, it's gonna be section 2.6. Okay. And don't worry, I will be hosting another one at 7:30 today, right? So you guys have more time to ask questions or to come up with questions, right? So don't worry about not having the time right now. Okay, so finite square well in the Griffith's book. And if you guys are curious about this, the free particle, right? Free particle, which is the particle that is supposed to be bound, right? But it has more kinetic energy than the potential energy of the bound well, right? So that's why it's called a free particle. It's also in the same book. It's in section 2.4. Okay. So read, like skim through it a little bit. And yeah, and then we can go on. Okay. So that is question 16. I think. Have I solved the entire thing of yeah, so the sum of the kinetic and the potential correspond to what? To total energy, right? The Hamiltonian, right? And that's it. It has to be conserved. And so if T decreases here, V has to increase, right? And vice versa. Okay. Um, Kala, I'm sorry that I cannot go through all the problem right now. I will be going through 18 and 19 later. Can you make it at 7:30? Okay. Yes, I will try to do that. And by the way, I'm gonna try to do some. I'm gonna spend like maybe 20 minutes to try to think of some good qualitative question for maybe chapter one, two, and a little bit of chapter three in the Griffiths book. And then I'm gonna ask you guys that a little bit later at 7:30. If you guys are still around, I can ask that question, and you guys can, think for yourself, like do a little bit of mental checking to see if you guys understand the materials. All right? Yeah, but oh, I don't know. I don't know. But like, I mean, I think in my opinion, it's just the same thing. If they okay. Yeah, if he says one-sided, just decrease the font size by half, right? And you have two-sided. Yeah. So yeah. Okay. So any other questions before I end the first section? By the way, the second section is gonna be like 1 hour and 30. Yeah, no worries. No worries. Yeah. Yeah, I will. I will after this. I have to find it though. I have to find it. I think I got one for. I'm not sure. I got one for the class I recently took, but I took this class like 2 years ago, so I'm not sure. Yeah, for so usually it looks very messy. I can show you guys. Yeah, so something like this. So usually like this is my cheat sheet for EC774, which is material or not materials, semiconductor structures. Right? It looks very messy, right? But I can take a picture of such a thing. I can send it to you guys. Yeah, if you guys can read it though. Yeah, I will. I have to find it though. Okay, right. Any other questions? All right, I'll end it now. I'll try to log in to get some work done, and then I'll get back to you guys at 7:30. Deal? All right. See you guys. Yeah, no worries. All right, see you guys later. Yeah, take care. Thanks.